This is Math 432, Applied Combinatorics. I am Professor Isaf, and today we are going to be discussing the 7 bridges of Konigsberg. Behold, the town of Konigsberg as rendered by Adderley. Through Konigsberg runs the river Pregel, and in the middle of it there is this large island. The river forks over here. There are 7 bridges in Konigsberg, as you can see here and here. Suppose that we want to walk across the 7 bridges of Konigsberg. This was a problem that the children of Konigsberg would often pose. How can I do it? So if I start here, I want to end here as well, but I want to do it Indiana Jones style, which means never cross the same bridge twice. Just imagine you blow up the bridge as you pass it, and so you never want to cross the same bridge twice. So we could take a walk, and maybe we'll leave Gingy here, and maybe we'll take this bridge first. Okay, now we're here. Okay, he'll come with us. Now where can we go? Well, we've got 4 different options. So maybe we'll exit this bridge. And now we're on this side of the river. We could walk all the way over here to the castle. And then we could cross this bridge next. Now we're here with the cow. And maybe we'll go ahead over here, this bridge. That'll be the 4th. We're back to our side. You might see that we're kind of in a little bit of trouble now, but okay, this is the only bridge we can take, 5. Now we have 2 options for the next bridge, and either way we're screwed. So we can cross here, and now we're stuck on this side with no way to get to this bridge and no way to get back to where we want to be. So we failed. We definitely didn't do it this time. But why? And, you know, there are lots of different ways we could think about doing this. There are a total of 7 bridges in Konigsberg. So if we just took all possible orders of the bridges, of course we can't always walk them. For example, you can't do this bridge followed by that bridge, right? So not all 7 factorial orders of taking the bridges are possible, but even so, 7 factorials just a bit over 5,000. So we could just run through all the possibilities. And it turns out that you can't do it. There's no way for the gingerbread man to walk across each bridge exactly once and end up back where he started. Actually, it doesn't even matter if you want him to end up where he started or not. He still can't do it. And the question is why? And this problem posed in the 1700s led Euler to discover, rather invent, depending on how you want to think about it, graph theory. So the idea is that we want to take this problem and simplify it. So here is a simplified model of Konigsberg. And here's a statement of the problem. The 7 bridges of Konigsberg problem asks, given this configuration of these 7 bridges, how can I cross each bridge exactly once? The way that Euler thought of this is we're going to represent each of the land masses as a vertex on a graph. So there's this top one, which we'll draw here. There's the center island, which maybe I'll put here. There's the lower half here. And then there's this little landmass over here. So we have 4 land masses that we're walking between. And how can we get between them? These are going to be the edges of the graph. So I can see that from the top to the center island, I have 2 bridges. So I can represent that as a multigraph. A multigraph just means that I can have more than one edge between any pair of vertices. From the center island, there are 2 edges going to the island at the bottom, the big landmass at the bottom. From the center island, there's one going to this sort of locked mass, which is over here. From this locked mass, there are also a bridge going to the north and the south islands, or land masses. So you can check that I've got 7 bridges marked here. And so now the question that we're asking ourselves is, given a graph, can you find an Eulerian path? So that's the term that we now give to these. An Eulerian path crosses each edge once and only once. So a walk in a graph crosses edges exactly at most once. So if I take a walk, I can sort of walk around like this and take 4 edges. That's a perfectly good walk. As long as you don't take the same bridge twice, it's a walk. Again, think Indiana Jones style. You blow up the bridge as soon as you cross it, so you can't take it again. So if we do that, that's a walk. So we can take a walk on this graph. Maybe we'll take our numbers for a walk. I could start here. I could take this bridge, and then I could take this bridge, and then I could take this bridge, and I end up back here, and that's a closed walk. I've ended up where I've started, and I haven't ever taken a bridge more than once. I haven't taken an edge more than once. But it's not a path, because a path has to take every edge. Here I've left off 4 edges, so it's not a path. So we want to ask ourselves, well, how can we do this? Can we do this? When can we do this? And of course, because it's combinatorics, we want to take some examples. So now that we've rephrased this in terms of a graph theory problem, let's just look at each of these examples and ask ourselves, can we do it? So I'm going to always start in the top left corner for each of these, and I'm going to ask myself, is there an Eulerian path? Again, I need to take each edge exactly once. So starting here, I'm going to take this one, so 1, and then I can't take that one again. I'll take 2, 3, 4. Yes, this one works. There is an Eulerian path on this graph. What about this graph? So here I'm going to start here, and maybe I'll start the same. 1, 2. Okay, we could take this guy 3. You know, I'm up here again. 4, 5, and this is no. It's not a closed path because I end up here, and I started up here. So I haven't ended where I began. So in that sense, the answer is no. Okay, what about on this graph? Again, I could start here 1, 2. Now I could take this edge and then, well, I'm kind of screwed, right? I can go up here and take 4, or I can go down here and take 4, but now I end up here. And now not only am I not where I started, but I haven't taken every edge. And if I had taken that edge instead, I wouldn't have crossed every edge. So no, there's not an Eulerian path here. What about this graph? This is an interesting graph. Let's do this one. Okay, 1, and now I'm gonna jump around and take this guy. 2, now I'm all the way over here. 3, I've gone up. 4, I'm gonna take this diagonal, and I was so close. But I've ended up here, and I haven't taken that edge. I have failed. But just because I failed with the way that I did it once, does that mean that there's no way I could have done it? That's what we really want to be thinking about. Which of these where I failed, is it because of my failure to take that right path? Or is it because it's impossible to do? That's the real question. So we'll take here, and let's say I'll take this loop first. And now I'll go here. You can see that actually adding loops doesn't make it more complicated. So we can ignore loops when we're doing this sort of problem. So let's go here. 3, and then 4, and then I'm going to traverse back 5 and 6, and did not work. But again, why didn't it work? Did it not work because I messed up, or because it's not possible to do? And this is Konigsberg again. And we cannot cross Konigsberg. So think about these examples. This one we could do. Is there a way that you could add an edge to the ones where we failed? For example, here, I've died out, right? I've lost it. But if I added an edge, and maybe I'll add it in a different color. If I added an edge around here to get myself back, that would let me do it. So why does adding that edge allow me to help? And what properties do we get of the ones that work versus the ones that don't? So if you play with a few examples, you might be able to build some intuition and get some insight. And in the next 2 videos, we'll prove the theorem that Euler proved, which is when you can and when you can't have an Eulerian path.